So in this video, we're going to consider the forces that are acting on the two objects in this diagram. This diagram shows a 10 kilogram object on an inclined plane, where the inclined plane is inclined at an angle of 32 degrees. And it's tied by a rope that goes over a pulley, and the rope is connected to a 4 kilogram mass that hangs vertically. And what will happen is if we let go of these two objects, the 10 kilogram mass will slide down the incline and the 4 kilogram mass will be pulled upwards. So we're going to start by looking at the forces that are acting on each of these objects. We'll start with looking at what's going on with the 10 kilogram object. So the first thing that we're going to do is draw what we call a free body diagram. The free body diagram is going to treat the 10 kilogram object as if it is a single point, a point mass, and then it will show the forces as arrows that are acting upon that point mass. So here's the beginning of our free body diagram. What we have here is an x-axis that's inclined, and the y-axis is perpendicular to it. And if we notice, if we draw a line here that's horizontal connected to the x-axis down here at the bottom, we'll make it dashed. What we want to notice about that is that angle that the x-axis makes with the horizontal line is 32 degrees. So in other words, that angle is the same angle as the angle of the incline on which the 10 kilogram mass is sitting. Okay, so we're going to put a dot at the, let me try that again. We'll put a dot at the center of our coordinate axis system. That dot represents the 10 kilogram mass. Okay, and so the question is, what forces are pushing and pulling on that? Well, if we go back and look at our diagram, for one thing, we notice that the rope is pulling up to the left. Another thing that we'll note is that gravity is pulling straight down. And a third thing we note is, and this is true of any object that is sitting on a surface, the surface pushes perpendicularly on that object. It's kind of like when you're sitting in a chair, right? Your butt is in the chair, and the chair is pushing on your butt. It's pushing up. Your butt's pushing down on the chair, but the chair is pushing up on your butt. So likewise, with the 10 kilogram object, right, it's being pulled down by gravity, but at the same time, the surface of the incline is pushing up. Now that up push is called the normal force, and then the force in the rope is called the tension force, and then we have gravity, which is called the weight. So those are the three forces that are acting on this object. And we're going to show in our free body diagram each of those forces. Okay, so we've got the normal, oops, try that again. Okay, that's a little better. So we've got the normal force that's pushing up like that. We've got the tension force that's pulling along in this direction. So here's the tension force pulling that way. And then we've got gravity that's pulling down like this. So those are the three forces, right? And you see those three forces are now, two of them are along axes. One of them is on the x-axis, although the negative x-axis, and the other one is on the y-axis. So notice how that compares to our original considerations of the 10 kilogram mass. So let me write in the names of those forces. The normal force is pushing in the positive y direction. The tension force is pulling in the negative x direction. And the weight force is pushing it's pushing vertically, or pulling vertically downward. Okay, now here's something to notice about this. Another aspect of this is that at this dot where we've drawn the 10 kilogram object, if we turn that into a dashed horizontal line, we'll notice that that too forms a 32 degree angle with the inclined plane. Okay, and if we do a little bit of simple geometry here, right? You know that this 32-degree angle and then this other angle here, those two angles have to add up to 90 degrees because the x-axis is perpendicular to the y-axis. So those two angles have to add up to 90 degrees. So what do we add to 32 to get 90? And the answer is 58. So that has to be 58 degrees. Now, here's the thing, though. We can use this thought to figure out what this angle down here is. Let me try drawing that again. There we go. Okay. What we know is that between this dashed line here and the vertical weight force, that angle is also 90 degrees. So we have 58 plus this blank angle between the weight and the y-axis. That means that this angle here has to be 32 degrees. So how about that? We know that the weight vector, although it's hanging vertically, it makes a 32-degree angle with the negative y-axis. And that is quite helpful. Okay, the reason that that's helpful, and let me get rid of some of these marks. There we go. Okay, and so you figured out that this is 32 degrees. Okay, what we're going to do is we are going to make a right triangle out of that weight vector. Okay, so the weight vector is going down vertically like this. Okay, but it is made up of two components that look like this. Okay, so here we have the weight vector, and this is the 32-degree angle. I'm kind of running out of room here, but that's 32 degrees. Okay, and so this is going to be the opposite side . That's the opposite side of the triangle, and this side over here will be the adjacent side of the triangle. And so we're going to want to figure out what the opposite side is and what the adjacent side is. So let's go up here. What we're going to use is SOHCAHTOA. And so the first part of that says that the sine of 32 degrees is equal to the opposite divided by the hypotenuse. Right? Now, another way we can write that is that the hypotenuse multiplied by the sine of 32 degrees is the opposite side of the triangle. Likewise, we can use the CA part of SOHCAHTOA for the adjacent side. We know that the cosine of 32 is going to be equal to the adjacent divided by the hypotenuse. And another way that we can write that is the hypotenuse multiplied by the cosine of 32 is going to be equal to the adjacent. Now, in both cases, notice that we need to know what the hypotenuse is. And the hypotenuse is the amount of the weight vector. Now, it turns out that the weight vector is going to be equal to m1 times the acceleration due to gravity, m1 times g. Now, if we go back to our previous drawing, we notice that m1 is equal to 10 kilograms. Okay, and we also happen to know that g, the acceleration due to gravity, we're going to use 9.8 meters per second squared for the acceleration due to gravity. So then the weight, the hypotenuse for the weight is going to be equal to m1 was 10 kilograms multiplied by 9.8 meters per second squared, and 10 times 9.8 is equal to 98 newtons. I'm going to use N to represent newtons. So, and this is going to be equal to the hypotenuse of our two triangles. So in our next slide, what we're going to do is we're going to make a chart showing the x and y components for these vectors. So let's go to our next slide. Okay, and we have our, going to make 3 columns. Okay, and the first column is going to be forces. The second column will be x component, which will be abbreviated as x comp. And then the third column will be the y component, which we will abbreviate as y comp. And so we're going to need a row for the tension force, we're going to need a row for the normal force, and we're going to need a row for the weight force, and then we're going to need a row for the total. And the total is we're going to add things up. And let's go back for a moment. I'm going to give myself a bit more room. Oops. I'm going to give myself a bit more room before I get to the total row. Okay, so our forces were, let's take the normal force first. The normal force is the force from the surface that's pushing perpendicularly on the block. Now we said it had 0 x component and that in the y direction it was F sub n. So that's our normal force. Now for our tension force, we know that it was pulling, let's go back to our original diagram, it's pulling upward, which means to the negative x-axis. It's pulling up to the left, so that's going to be negative t, and it's not pulling in the y direction. So we have those forces so far. Okay, and then we're going to talk about the weight. Okay, now the weight, as we said, the weight is equal to mg. Now the x component is going to be the part, okay, the x component is going to be the part that pulls in the x direction, and the y component will be the part that points in the y direction. So the x component is the part that we used with the sine, and it's going to be equal to the hypotenuse multiplied by the sine of 32, and we know that the hypotenuse is 98. So let's go to our next here, and we'll say that this is going to be equal to 98 times the sine of 32 degrees. Okay, and that's positive because it's pulling downward in the positive x direction. So let's get a numerical result for that. So we have to take the sine of 32 degrees, and then we're going to multiply that by 98, and we get 51.9. So that is our result. We're going to round off to the nearest tenth, and that's our result for the weight in the x direction. Now if we go back here, the weight for the y direction is going to be the adjacent side, which is the hypotenuse times the cosine of 32. But notice that it's in the negative direction. So that's going to be negative 98 multiplied by the cosine of 32. And so we'll multiply that up. First, we're going to get the cosine of 32. And then we'll multiply that by 98. And we get negative 83.1. Okay, so that's what we have so far. Now, here's the thing. Okay, if this block is going to move, it's going to move down the incline. It's going to move in that direction. And what's going to cause it to move is the force that's pulling in that direction. Okay, so a force is pulling it down in that direction, and the force that's pulling it down in that direction is going to be a combination of the weight force that's pulling in that direction minus the tension force pulling in that direction. And in any extent, or at any rate, the total amount of force, and that funky looking sideways M, is a summation symbol. So it means the total sum of the forces, the adding up of the forces, is going to be equal to the mass of the object multiplied by the acceleration of the object, which is Newton's second law. So we have Newton's second law. So how does that work in our chart? Well, in our chart, what this means is that this is going to be M1 times A, where M1 is 10 kilograms, so that's going to be 10A. In the y direction, the forces are going to balance. This object is not going to accelerate in the y direction. If we look at the original drawing, there's no way that this object is going to lift off the inclined plane and fly off into the y direction, or burrow down through the inclined plane and travel in the negative y direction. That just will not happen. So this object will not travel in the y direction. It will only travel in the x direction. And since it doesn't travel in the y direction, we can say that the summation of the forces in the y direction is 0. So now let's put all this together, okay, and we're going to add up each column. So let's go to the next slide, and we're going to look at what happens in the x direction, and we're going to look at what happens in the y direction. Okay, in the x direction, if we look at our values, we have negative t, we've got positive 51, and those are going to be equal to, this last line should be thought of as an equal sign, that will be equal to the total. So we're going to have negative t plus 51.9 equals 10A. So we get negative t plus 51.9 is equal to 10 times A. So that's what we get in the horizontal x direction, not exactly horizontal, but in the direction of the incline rather. Okay, so that's what we get in the direction of the incline. And then in the y direction, if we have f sub n minus 83.1 equals 0. So f sub n, f sub n minus 83.1 equals 0. And that's good to know because that tells us that f sub n is equal to 83.1 newtons. We'll use the symbol, we'll use n to represent newtons. So that's 83.1 newtons. Now the other equation, negative t plus 51.9 is equal to 10a. We're going to save that away and use that a little bit later, okay, because we have another free body diagram to draw. Okay, now we've analyzed the 10 kilogram mass. We drew the free body diagram. X was in the direction of the inclined plane, Y was perpendicular to the inclined plane, and we drew the three forces. So now we're going to draw another free body diagram, and this time we're going to make it vertical. And so X will be horizontal, Y will be vertical, and this is for the 4 kilogram mass. So what we're talking about here is the 4 kilogram mass, which is right here. You'll notice that it is hanging vertically. The tension is pulling up, but gravity is pulling down on it. So we're going to have those two forces, tension pulling up. This is going to be tension. And by the way, it's the same exact tension as the horizontal tension because it's in the same rope, right? Both of those are in the same rope. So the tension in the rope is the same throughout the rope. So let's go make that chart, or let's go make that free body diagram. So we're going to have the tension, whoops. So we're going to draw a dot. That dot represents our mass. This is for M2, and M2 is 4 kilograms. And we want to remember that G is 9.8 meters per second squared. Okay, so we have the tension force pulling up, and we've got the weight force pulling down, but this weight force is going to be equal to M2 times G. Okay, so we only have those two forces, and so once again we're going to make a chart, right? Every time we do a free body diagram, we also do a chart. So let's draw our chart. Our chart will have 3 columns. The first column will be forces. The second column will be the x component. And the third column will be the y component. So we will have one row for the tension force, and we're going to have another row for the weight force, and then we're going to have our total at the bottom. Okay, so we have our tension force. And if we go back and look at the diagram, the tension is not pulling in the x direction at all. It's pulling in the y direction. So the x component for the tension is 0. The y component is positive t. And then our second force is the weight. Okay, and the weight is pulling down, and we recognize that it's M2G. M2 is 4 and G is 9.8. So it's going to be M2G, which will be equal to 4 times 9.8. And we're going to calculate that. Oops, I'm putting that in the wrong place. Excuse me. The x component of the weight is 0. Just checking to make sure you're paying attention. Okay, so the x component of the weight is 0. It's the y component of the weight that is M2G, and we want to notice that it's actually negative M2G, and it's negative because it's pulling down. So M2G is going to be negative 4 times 9.8. And let's calculate what that is. So 4 times 9.8. And so we get negative 39.2. So negative 39.2. Now in the x direction, the object is not going to accelerate, so that total will be 0. But in the y direction, if we go back and look at the original picture, we expect the 10 kilogram force to move down the incline to the right, which means that the 4 kilogram object is going to move up toward the pulley. So that means that the acceleration for this object is going to be positive m2 times a, and that's going to be equal to m2, which is 4, times a. Okay, so all of our analysis for this object is in the y component. So we have the tension, which is positive. We have negative 39.2, which is pulling down. And then that's going to be equal to, because that last line needs to be thought of as an equal sign, it will be equal to 4a. So let's write down that equation. And so we get t minus 39.2 is equal to 4a. So that's another equation that we've got. So let's write down the two equations that we have by analyzing this entire system. We have the one that we just did, which is t minus 39.2 equals 4a. And let's go back a few slides to figure out what that other equation was. Here it is right here. Right? It's negative t plus 51.9 is equal to 10a. Negative t plus 51.9 is equal to 10a. So we have two equations. This is a system of equations. We have two equations, two different equations, and we have two different unknowns. Right? We don't know what t is, that's an unknown, and we don't know what a is, that's an unknown. So we're going to try to figure out what they are. And the easiest way to do that, in this case, is we're going to eliminate the variable t. And we're going to do that by adding these two equations together, term by term. So starting with t, in the first equation we have positive t. In the second equation we have negative t. If we add those together, t plus negative t gives us 0. Okay, that's cool. Okay, now the next thing that we're going to do is we're going to add negative 39.2 to positive 51.9. And we add those together and we get positive 12.7. And then on the right side of the equation, we're going to add 4a to 10a, which gives us 14a. So what do we got? We have this equation. We have 14a, we've got 14a is equal to 12.7. So we're going to divide both sides of the equation by 14 to get the acceleration. And that's going to give us 12.7 divided by 14. So 12.7 divided by 14 is equal to, the calculator says 0.9071. We're going to round this off to 2 decimal places after the decimal point. So this is going to end up being 0.91, and that will be in meters per second squared because it's an acceleration. So we know the acceleration is 0.91 meters per second squared. Okay, so now that we have the acceleration, we can go back and figure out what the tension is. So we're going to rewrite, whoops, I went backwards. Oops, what did I do? Okay, well, I've got t minus 39.2 is equal to 4a. Okay, well, we'll use that. Okay, and I know that this means that we have t minus 39.2 equals 4 times a, but a is 0.91, which is what we just calculated a moment ago, 0.91 meters per second squared. So this gives us t minus 39.2, and now we're going to do 4 times 0.91. And 4 times 0.91 is 3.64. And then we'll solve for t by adding 39.2 to both sides of the equation. Right? We want to get rid of the 39.2 on the left side of the equation, but it's negative 39.2. The opposite of subtracting 39.2 is adding 39.2. So we're going to do the opposite. And whatever we do to one side of the equation, we have to do to the other side of the equation. So on the left side of the equation, the 39.2's cancel, and we are just left with t. On the right side of the equation, we're going to add 3.64 plus 39.2. And we get 42.84 newtons. And so, by doing this whole method, we were able to calculate the acceleration at which the object would be moving, and we were able to calculate the tension that was in the rope that goes over the pulley. So hopefully this was helpful. We used the free body diagram method where we showed all the forces, and then we added up the forces in the x and y direction. We also used Newton's second law, F equals ma, and that was able to help us figure out what the tension and the acceleration had to be. So I hope you found this helpful, and we will talk about this some more, of course.